Okay, thank you. Good morning, everyone. Today's topic is anomaly detection for smart aquaculture. I will discuss predicting water color changes in grouper ponds based on our publication last year in the Journal of the World Aquaculture Society. Although Gary, the first author of the paper, couldn't join us today, I will do my best to present this work. Okay, I am Kuan Chang from National Taiwan University. This talk does not focus on the hardware of an IoT device. Instead, it delves into the analysis and software aspects of IoT. The outline of today's talk, we will first go over why aquaculture matters, why Taiwan is good at grouper farming, and what the problem we are facing, and what we propose to solve it, and the result we got, and the conclusion and the future directions. Okay, so what can you recognize from this image? This image offers insights into large-scale aquaculture practice in Taiwan. The air view depicts a coastal area with a grill of large rectangular aquaculture ponds. The varying shades of green suggest different level of presence of algae. Because their proximity to the coast, these ponds use seawater for farming. Okay, consider our audience. So we will begin by highlighting the significance of aquaculture. According to the most recent State of World Fishery and Aquaculture Sophia report by the Food and Agriculture of the United Nations 2 months ago, aquaculture has, for the first time, exceeds capture fisheries in aquatic animal productions. Okay. So, what's the relationship between grouper farming and in Taiwan? And Taiwan is often referred to as the kingdom of grouper fish. It had the highest production value globally, approximately reaching 33%. The predominant grouper breeds in Taiwan are green groupers and giant groupers. The key to success in grouper farming in Taiwan lies in strict division of labor. The breeding process is divided among several families, with each family responsible for one specific stage, including parent fish cultivating, egg incubation, fry breeding, group fish pairing. This process decreased the breeding risk for the farmer. Moreover, Chinese feast often feature grouper fish. Grouper meat is not only tender and delicious, but also rich in nutrition. For example, giant grouper is a very high quality white meat fish that grows quickly, reaching 15 to 25 kilograms in 3 years, versus the growth of a salmon to 4 to 8 kilograms in the same period. Okay, let's review some biology about groupers. Groupers have more than 160 species. Many of these species have large mouths and heavy bodies. They can grow up to 3 meters in length and weigh over 300 kilograms. Groupers are carnivore, feeding on other fish, squids, and crustaceans. Groupers are relatively long-lived. Some in captivity has lived for more than 30 years. Certain grouper species can transform from female to male as they mature. Unfortunately, several grouper species are listed as vulnerable or threatened due to overfishing and habitat loss. Okay, back to fish farming. Water quality is very important. Water quality plays a crucial role in aquaculture ponds. Cultivating algae and other microorganisms is essential for water quality, for maintaining oxygen, nitrogen cycles in aquaculture ponds. To assess algae and microbial growth, the most straightforward method is visual observation of water color. When the green algae rich in chloride dominate, the pond appears green. When diatoms containing carotenins and lactophiles prevail, the pond appears brown. If algae in the aquaculture pond die off massively, the water becomes clear and transparent, commonly known as algae bloom crushes. Unfortunately, if algae die off in large number, fish in the pond are highly susceptible to harm. So in the past, grouper farming relies on empirical methods. Grouper farmers will access and make adjustments to their aquaculture ponds based on observation of water color. So on the right side, you will find the favorite color of a grouper farm, which is green. Meanwhile, the left side displays an unfavorite color, which is brown. So here we were trying to transform empirical method into a scientific method. The immediate goal of this study is to investigate the relationship between water quality anomalies detected through monitoring and the changes in water color within the grouper ponds. The long-term goal is to establish autonomous fish farming systems with real-time monitoring and interventions. Okay, so converting this empirical method to a scientific-based one isn't straightforward. Specifically, detecting changes in water color is challenging due to limited data. Okay, standard supervised machine learning technique won't work here. So our proposal is to import anomaly detections. So anomaly detection is crucial in data analysis and machine learning. Okay, it's like the detective work of data science. It detects mystery data points that deviate from the usual pattern. For example, consider the credit card fraud. Consistent routine spending followed by an unusual large expense at nightclub. This is a hint of a potential fraud. Okay. However, we didn't know whether changes in water color can be considered water quality anomalies or not. Okay. We found out some solution, this anomaly detections. The state-of-the-art anomaly detections has been successfully applied to water quality monitoring for different water sources. For example, the drinking water, a logistic regression approach excels in detecting water quality anomalies, and LSTM improved its performance. So how we propose to build a long short-term memory models. So how we build the computational model? The standard neural networks struggle with a long-range dependency. To address this, long short-term memory (LSTM) networks use Gates mechanism to capture such dependencies. So both LSTMs and transformers excel in natural language processing and complex sequence modeling. However, LSTMs require less computational and memory resource compared to transformer, making them suitable for scenario with a limited resource. LSTM utilize a recurrent structure with a cell to regulate the information flow. The cell, a fundamental component of LSTM, functions as the network's memory, retaining relevant information during sequence processing. So h of x represents the input, where each input contains n features. T denotes the time step. H of t corresponds to the output of the hidden layer. Okay. The forget gates decide what information is discarded from the cell. The input gates update the cell with new information. The output gate decides what next hidden state should be. So we conduct this study on 6 grouper ponds in Pingdong, Taiwan. Taiwan is situated adjacent to mainland China, Japan, and the Philippines. Pingdong is the southern part of Taiwan. Okay, it's a tropical region. Fangliaotang, okay, is where the study took place. Fangliaotang of Pingdong is known for its grouper farming. Okay. The daily monitoring of the fish farms records feed intake, water temperature, salinity, pH value, nitrogen dioxide, ammonia, dissolved oxygen, water color, and the use of the drugs from March 2018 to December 18. We select water temperature, salinity, and the pH to study here, as these 3 parameters has the most complete records. So our goal was to create a computational model for predicting outcomes in grouper farms. Before diving into this, we analyzed the data and uncovered some key findings. Specifically, we explored the relationship between air temperature and the pond water temperatures. So the x-axis here is denoted the time. Y-axis represent the temperatures. They can be either the water temperature or the air temperatures. So basically, when it rained, the air temperatures experience a sharp drops. On raining days, the maximum air temperatures can even be lower than the water temperatures. So in our studies, we observe a stronger correlation between water temperatures and the yesterday air temperature compared to the air temperature of today or 2 days ago. This suggests water temperatures changes more slowly than air temperature. We also analyze the characteristic of a grouper ponds with a green and a brown color. As you see here, our study of the 6 grouper ponds consistently revealed that on average, the brown grouper ponds exhibit higher water or air temperature than the green grouper ponds. However, the trends in pH or salinity were less consistent. So the test here is we want the model to predict the next day's value. So the models took 3 consecutive days of value to predict the next day's values. We built 1-layer LSTM network with 7 cells. The activation functions is ReLU. The loss function is mean square error. The optimizer we use is stochastic gradient descent. The data, the features include 6 kinds of observation. That is water temperature, pH value, salinity, air temperature, air pressure, and rainfall. The training data consists of 120 days records, and the test data is the rest of them. By the way, we found the multivariate models works better than univariate models in our case. So let me walk through a simple example. As illustrated here, there are observations from March 2018 to December 2018. This one is water color, and the other one is water temperature. The orange curve represents the true water temperature. The red bands denote the anomalous. So how can we detect the anomalous? So basically, we calculate using the absolute value of the difference between the predicted value and the true value. And the value has been on the top 5%. So we use the precision ad hoc record and ad hoc H1 H1 score. So for the detail about the ad hoc and the H1 score, please refer to our paper. Basically, the result told us the top 5% of water temperature anomalies successfully predict over 40% of water color changes. This is much better than the random guessing. And we also find out, according to the F1 IR scores, pH anomalies are the most likely sequence to the water color changes, covering at least a quarter of the changes. So in conclusions, it is possible for water quality anomalies to pertain water color change. And water temperature anomalies are highly effective in early detection of undesired color changes. Targeting the top 5% water color anomalies predict over 40% color changes. And pH anomalies occurs after the color changes, indicate the consequences. Okay, so for the future applications, an early warming system can lead to proactive actions, including efficiency and susceptibilities in fish farming. Here, I want to thank to the Digital Agriculture Committee for giving me the chance to present the work. And this is our lab. And Gary is the first author of this work. And this is our collaborator. And also we want to thank Longdian biotechnology company for collecting the monitoring data. Okay. Thank you for your attention.
Thank you very much for that interesting presentation, Kuan. We have time for maybe one quick question. Yep, please go ahead. I was wondering if you said that the data is rare enough that you have to take an anomaly detection approach. I was wondering if the research group, considered trying to enrich the data with other types of events. So let's say the incidents of health issues with the groupers, or other data as opposed to only the environment temperature, maybe the temperature that the water comes in before being fed to the ponds. If you consider enriching your data set with other types of attributes, or if there are other types of attributes you could think that the data could be enriched with.
That's good questions, but we haven't thought about to enrich the data set because we find if we enrich artificially data into the data set, actually they will decrease the performance. So we prefer to use the real data sets. Thank you.